So just a few more things about substitution today so that we can move on to parts and then just come back to substitution later because it shows up a lot more. Let's take a look at yesterday's problems. The last couple of problems from yesterday showed us one of the things that we can do with this substitution business. In the first example, integral of x square root of x minus 3. We made the substitution w equals x minus 3. That not only allowed us to rewrite the square root of x minus 3 as the square root of w, but we were also able to deal with the x out in front. That x was not part of the dw, so it's kind of a leftover x that we have to deal with. But because we make the substitution w equals x minus 3, we can rewrite that and replace the x with a w plus 3. So we were able to get a little bit more mileage out of our initial substitution. So that led us to an integral entirely in w, and we were able to use the distributive property and move on from there. The substitution worked. This part of the integration is not the important part of the integration. What we're studying right now is going from an x integral to a w integral. The parts that we need to make that work. Then the next example, the one that we left undone yesterday, had a similar setup. I've got a square root of x squared minus 3 with another x squared out in front. And the question was, why can't we do the same thing here that we did in the other one? So it seems that we should be able to make the substitution w equals x squared minus 3 and rewrite that to say x squared is equal to w plus 3. And then the question was, why isn't this gonna work? Why can we not do that in this scenario? So here the question was, we wanted to point out that this is not gonna work. Why can't we do this? So why is it that this is not why is this not going to work? So you can see that this is not going to work because of the stuff that I didn't write. What did I not write yet? dw. What do we need for the dw in this integration? I need 2x dx. So I don't have an x squared to be a w plus 3 because one of those x's has got to be my dw. I need one of those x's to be the dw. So this is not going to work because I need one of these x's to be a half a dw. So in this case, we don't have enough x to do this extra substitution. We can replace the x squared minus 3, but we won't be able to replace that other x squared because there's only one left. We've only got one spare factor of x because one of those factors of x squared has to be the dx. Sorry, the dw. This is why it's important that we don't just assume that things are going to work the way we expect them to work. Question? So if we rewrite this problem again to an integral of x cubed times x squared minus 3, now we're back to being able to do a substitution and do our stupid substitution trick where we reuse our w. where we rewrite the W in terms of, rewrite the W to get another expression for the X. Now I've got 3 extra factors. One of them is going to be my dW. The other 2 can be converted into W as well. So now this trick will work. So if W is equal to X squared minus 3, I can replace an X squared with a W plus 3. And dW is 2x dx. So that's we still have a factor of x to be our dW. In the previous example, all we had was x squared. We need one of those factors of x to be the dW. We don't have anything to do with that extra 1 factor of x. In this new example, the x cubed has 2 factors of x that we can turn into x plus 3 and 1 factor of x to be the dW. So we're looking at this x cubed as an x squared times an x. So my substitution will work. This x squared can be replaced with a w plus 3. My square root of x squared minus 3 can be replaced with the square roots of w. And my dx, this x and the dx can be replaced with 1/2 dw. So having that x cubed out in front makes this look like our original problem at the top of the page. Notice that all that happened was we have that 1/2. And those extra powers of x, the x squared is contained in that w. And here we can proceed as we did before. Any questions? The important thing to note here is that when we want to make this, when we want to double use a substitution, when we want to use a substitution in both directions, our exponents have to work out. So in the first example, w is x minus 3, and then x is equal to w plus 3. I had x to the first power. We had that piece. In the third example, w is equal to an x squared, so x squared is equal to w. I can only replace those x's in pairs. So in the previous problem, we might think that we want to take that x squared is equal to w plus 3 and just solve for x to see what 1x looks like. But then 1x looks like a square root of w plus 3. And our problem is just going to get worse. So if you were thinking, why don't we just solve for one of the x's? The reason that we don't want to just solve for one of the x's is that the thing that we're trying to get rid of is 2 terms with a 1/2 power. That's super inconvenient because I can't just distribute. And if I try to solve for just 1x over here, it becomes a square root of w plus 3. So that messes everything up. So the outside x has to not just 1 power greater. In this case, 1 power greater because the substitution we're making is an x squared. And so I need that extra x to be the dw. Perfect question, by the way, because my next example Let's suppose that inside I have a square root of x cubed minus 2. I'm just going to trade those. What do I need to be the dw? Because the obvious substitution that we'll want to make here to make this substitution work I'm going to need a dw. If our inside is x cubed minus 2, if the substitution that we want to make is x cubed minus 2, now I need x squared to be the dw. So now outside, I can have an x squared, or it can be bigger than that by 3, because I can only replace x cubes with expressions in w without introducing radicals. So if we want to resubstitute, if we want to get more use out of our substitution, we can turn this x cubed into a w plus 2. So the powers of x that will work are 2, and that, or more than that by 3, because x cubed gets replaced with a w without introducing radicals. So this x to the, I'm just going to do an infinite number of examples. Instead of putting it in terms of n, I'm going to put it in terms of the stuff that we see. So it can be a substitution if the x to the n part is x squared. That's going to be our base model substitution. That's going to be the one that shows up on quiz integration by substitution part 1, because it is super basic. There's the inside, derivative of the inside is right there. One level up from that, it could be that we have an x to the 5th. Yikes. If we have an x to the 5th, then I'll have x squared to be the dw and an x cubed to be w. I can only replace x cubed with w. Otherwise, I'm going to be introducing radicals, and we're trying to avoid introducing radicals. It doesn't mean that we don't have an integration. It just means that the substitution that we're attempting is not going to work. We can actually go further, because if we have x to, what would the next one be? I just said we can go further. What would the next one be? So remember what we need. The w's come out in 3s, x cubed. I need to have an x squared. The only way we can replace w's, replace x's with w's is when they're x cubed. I need 3 of them to make 1 full power of w. So if I have x to the 8, that would be 2x the x cubes. That would be an integer power of w. And then 2 of those x's to be the dw. So it has to go up by 3, so we get integer powers of w. So great question. It has to be greater than 1. It has to be greater. It has to be, first of all, a multiple of what we're trying to substitute. We're trying to substitute x cubed, so it has to be x cubed that we substitute w. Otherwise, we end up with radicals, integer powers of w. And number two, or the second part, is that it has to also include what we need for the DW. Any questions? This is way more substitution than you will ever need. No one is ever going to ask you a problem like this out of the blue and not give you a lot of time to think about it. You're never going to be sitting in a final exam and I might call integral of x to the 11th square root of x cubed minus 2. Because on the final exam, I put x cubed plus 1. I'm just kidding. That goes too far. You know what I mean? There's training and then there's application. Your training should always go further than you're ever going to need. How's everybody okay? To answer the other question, I do not know why I find integration so much fun. I think it's just because it's so weird. Differentiation is boring because we've got the 3 rules. We are 100% certified in differentiation. All we have to do is maintain our certification when new functions come along. So if you didn't do hyperbolic trig functions, it's like, well, here's hyperbolic cosine. And you're like, well, I don't know the derivative of that. And you find out it's hyperbolic sine. So I go, okay, your recertification is done because if you got hyperbolic cosine of x squared, you're just going to use a chain rule. If you've got the square roots of hyperbolic cosine of x squared, you're just got to have more chain rule. If all that's being divided by x to the 5th, it's going to be quotient rule with some chain rule. You're already recertified. If I change this integral to x to the 10th square root of x cubed minus 2, all of a sudden it's like, nope, that's beyond your pay grade. You're not certified for that integration yet. Any questions? The other part is that product rule, quotient rule, chain rule are describing the structure of what's going on. There's an operation that's being used to combine functions, and it always works. If you see multiplication and you're trying to find a derivative, product rule will always get you what you want. If there's a composition, chain rule will always get you what you want. Here, I have problems that are super similar. One of them is substitution and one of them is not. Integration is weird like that. Any questions? All right. Oops. Up next, integration by parts, which is the anti-product rule. Good news about integration by parts. There's a formula for it. Bad news about integration by parts. There's a formula for it. And that just means you have to remember the formula and how it works. This is what I think the most efficient integration by parts is. This is my, this is the one that works for me. So it's compact, doesn't have any extra stuff. So integration by parts is the integral of u dv equals uv minus the integral of v du. The integral of u dv is uv minus the integral of dv du. The integral of u dv is uv minus the integral of v du. I like the version of the parts formula without all the x's in it. I also don't bother showing you why this is from the integration by why this is the anti-product rule. Put the integral of v du on the other side and take the derivative all the way through. Derivative of the first times the derivative of the first times the second plus the first times the derivative of the second. That's where it comes from. We don't need to write that down. Because right now we're integrating. And I know you all know the product rule. And this looks different enough that you'll just remember the integral of u dv is uv minus the integral of v du. And keep thinking, Leach, you keep saying that. That's because I want this to be stuck in your head, and songs don't get stuck in your head because you hear them once. Any questions? Like that forever, now I don't even recognize the Lady Gaga song anymore unless it's sped up TikTok style. I heard like the original song, that song the other day, I'm like, oh, wait a second, this sounds something wrong. Is this slow? Oh no, it was sped up. Notice that there are 4 parts: u and du, v and dv. There are 4 parts. Over here on the left, that's the integral that you're handed. And so these are the 2 parts that you have to decide on. You choose which one is u, you choose a dv. So these are your given parts. Once you decide how you're going to split up your given parts, then you have to find the other 2 parts. I can't remember if I have 4 different colors. If I do this as a 4-color problem. So here's how we use the 4 parts. There's 2 that were given, and then there's 2 that we find. Then we put the 4 parts into the parts formula and evaluate what I will refer to as the secondary integral. So first step, choose your given. Second step, find the other two parts. Third step, drop into the parts formula. And fourth, evaluate the secondary integral. And then repeat. So first, you identify your givens. Second, you find the other two parts. Third, you drop them into the parts formula. Fourth, you evaluate the secondary integral. And fifth, repeat if necessary. This raises the question, how do we know we have to repeat this? You'll just know. Don't worry about it. This raises the question, how do we choose u and dv? Good question. dv has to be something that you can integrate. You have to know the integral of dv. Whatever you choose for dv has to be something that you can integrate. Whatever you choose for dv, dv must be an integral that you know. You've got to know that integral. Otherwise, you can't do the second step because you have to integrate dv to find v. Now, before you do any of this, you're going to want to make sure that this is going to require integration by parts. So your zero step, before you even start on this path, you're going to verify that this is not substitution. Once it's not substitution, then you can start this. One of the questions that's going to come up the more we practice each of these two types of integration, this anti-chain rule and anti-product rule, one of the questions that's going to come up is, how will I know which rule to use? And the answer is, don't worry about it, you'll just know. If a problem comes along and you're not sure, that just means you need to do more problems. And then you'll just recognize. This only feels like I'm trying to program a reaction into you because I'm trying to program a reaction into you. This only feels like it's not going to be useful in your future career as a fill in the blank, because it's probably not going to be directly useful to you in your future career as a fill in the blank. Not directly. We're not really sure how to quantify the indirect benefits. Let's look at an example. Classic integration by parts problem. The integral of x sine of x. Those of you who are wondering, there are going to be 3 more examples today. X sine x, x sine of x squared sine of x. one of them is not going to be a parts problem, because knowing the difference is an important aspect of it. So we have two parts. We've got an x and we've got a sine of x. So we need to decide something is u that we're going to take the derivative of, and another part is going to be a dv that we integrate. We're going to choose u is x. That's bad grammar. U are x, and dv will be the sine of x dx. This is a choice that I made. I said u should be x, and dv should be sine of x dx. Eventually, we're going to stop writing the dx in the dv part because we know that that's where it goes. But right now, we're being careful and including everything. If u is, that's the first step, making this choice. Second step, find the other two parts. The derivative of u, the derivative of x is 1 to x, and the integral of v dv is negative cosine of x. Don't worry about the plus c. Oh, I should put u as green, then it'll look like a substitution problem. Maybe I'll switch. Remember, the derivative of cosine is negative sine, so the integral of sine is negative cosine. Now that we've got the four parts, we can put these four parts together in the parts formula. The integral of u dv is uv, so negative x cosine x. Minus the integral of v times du. If you're looking at these extra parentheses around the cosine and say, ew, gross, why? It's because we're integrating that negative. And I didn't want to put the negative out in front right away. The blue doesn't show up against the black very well. This is what we would actually write if we're still at the stage where we're writing this, all the steps down. We might do something like, this one looks the same, negative cosine x times x. Notice that I split the product -1 and cosine x to put the x in between. If you write the x out in front, all of a sudden you're subtracting those two things. You turn one term, what should be one term, into two terms because you didn't use parentheses. And it becomes a whole thing. What we'll normally do is write negative minus the integral. And since our v has a negative in it, we know that that's going to change the sign. So I'm just going to factor it out, so I can drop all these extra parentheses. We're also not going to write 1 dx. We're just going to write the dx because the 1 doesn't need to be there. The reason I'm spending so much time on this is that we have to be really careful how we write this uv. I already started doing shorthand. I shouldn't. But that first term is going to be u times v. So if I just write x times negative cosine x, even though I said x times negative cosine x, I did not write x times negative cosine x. I wrote x minus cosine x. And all of a sudden, I've completely changed. In my mind, it was one thing, and what I wrote down did not match. This is why we want to get used to just moving the negative out in front of the term, so we don't have to include all these extra parentheses. This is also why I picked sine x for this example and not cosine x. I wanted that negative to show up. I wanted that negative to be a problem. So this is how we're going to deal with negatives. If there's a negative term here, we're going to split and stick that in the middle. If these were both negative, then I'll just cancel them out. If there's a negative that's going to be a factor in my integral, I'm just going to pull it out and change the sign out here. Multiply this, factor out the -1. So that was step 3. Do the parts formula. Step 4 is evaluate our secondary integral. The integral of cosine is sine, because the derivative of sine is cosine. Since we've done all of our integrals, we can write plus c. Yeah. So we had to make a choice. The two parts were x and sine of x. I had to pick one to be the thing I differentiate and one to be the thing that I integrate. One of the reasons that x is a good choice for the differentiate one is that x becomes 1 when we differentiate, and things get smaller. But also, excellent question. That raised the question, how do we know which one is u and which one is dv? Let's see what happens if we switch them around. You're like, oh, dude, I thought you said there were going to be 3 more examples. Like, well, this is still the same example. This is a 2-for-1 deal. Everybody likes it when you get a BOGO, right? And you're like, no, not when it's math problem. If we set this up with u equals sine of x and dv as x, because the only rule that I've given you so far is that dv needs to be something you can integrate, and we can integrate x. Then our parts are du, derivative of sine is cosine, and our integral of dv is a 1/2 x squared. Now in the parts formula, uv, that's no problem. 1/2 x squared times the cosine of x, or sorry, 1/2 x squared times sine of x. But the problem is our integral is now x squared cosine x. That's worse. We went from x to the first cosine x to x squared cosine x. Now, this is fine. This part is not. So our secondary integral ended up being kind of bigger than our initial. Because that x squared, we went from x cosine x to x squared cosine x. That didn't make anything better. We don't want our secondary integral to be worse than what we started with. At this point, what you do is say, well, this got worse, so I'm going to go back to my original and try switching those two things. That is the first step in troubleshooting a parts problem. Go try the parts the other way. Any questions? How's everyone, okay? You have to remember that part starts off with this choice. If you get stuck on a parts problem and you've only attempted it once, you're not stuck on the problem yet. If you get stuck on it, you're not stuck on a parts problem until you've attempted the problem at least twice. If neither choice of parts works out for you, then you can declare yourself stuck. But with these kinds of problems, the most important thing is don't be afraid to make a mistake. Don't be afraid to take the problem somewhere that it's not supposed to go. Does that make sense? You don't get to be afraid of making mistakes. I don't blame students for being afraid of making mistakes. The way that we usually apply education is we turn people into being mistake averse. But we have to end that. You all are going into science. You can't be afraid to be wrong. Because you're going into science, you're going to be wrong most of the time. That's how hypotheses work. You say, is it this? No. Okay, well, how about this? All right, so tomorrow we're going to continue our adventure in parts. We're going to put substitution on the back burner for a little while, just working on that in the homework. 7.2 homework, integration by parts. We're working on that. That's our new thing. Remember, if you're stuck on integration by parts, we've done one example. You're supposed to be stuck on integration by parts. You've done it once. Actually, you've done it none times. I've done it once. You've watched it happen one time. So don't let that get you down. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.